Do I hear any questions? Yeah.
I guess we don't have, when are you going to give us feedback on the project stuff?
Okay, I sent out feedback for the project stuff.
I just checked out, pulled everything this morning and I didn't an email?
Okay, yeah. So yeah, that would have been smart to put it in there, but I just sent an email. So check the email. And yes, I know I'm horribly late with homework for.
We didn't get any email regarding the project because there's nothing to do.
Yeah, because we've been in contact about it. So. Other questions? All right, so let's go on with this lecture on Clojure. And so Clojure is a version of Lisp for the JVM. And so you may say, who needs it? So I'll say right away why I care. The one reason that I care is it has this implementation of the software transactional memory thing. And I do care about that. So software transactional memory, as we'll see on next Tuesday, is another mechanism of dealing with concurrency. And it's implemented in Haskell, for example, which we don't really know, and it's a bit tricky to learn. And it's implemented in Clojure. And since we already have learned how to deal with Scheme, I figured Clojure was going to be the easiest way of doing it. But it does mean that I have to have an lecture on Clojure today. Why do we care about software transactional memory? It's the closest thing that we know to do kind of automatic management of memory in a concurrent environment. And you'll see what it does and what it's good for and what it's not so good for on next Tuesday. And I haven't actually checked how that maps up with the homework because you're going to have to use it for one of the homeworks. Whether I might have to extend that deadline. I'll ponder that. So what does it do? So other people like Clojure just because it's listed for the JVM, but you could probably fit those people into this room. So really the major attraction is the STM feature. So as you'll see, it's somewhat easier to read than standard Lisp. With it has fewer parentheses, it has a few other syntactical devices to make it a little easier to read, but it's not dramatically easier to read. There's macros, of course. It has a manual way of doing tail recursion. It lives in the JVM. It interoperates with Java, so you could just write all your Java code in Clojure if you so chose. And a small number of people really do like to do that. So I'm mostly going to focus on just what we need to do the software transactional memory next Tuesday. And I'm not going to talk about the other 20 features that it has. The basic Lisp syntax looks like you think Lisp syntax looks. In parentheses, operator goes up front. Arguments come after. And minor syntactical difference, when you want to define a function, you use defn. Saves 2 characters over Scheme, where you would use define. Name of the function. Then you have afterwards, you have in square brackets the argument list. We'll see later why that is. So the rest is the same. This stuff here looks completely like the others. Function application quotes, same as in Scheme. To show the fewer parentheses feature, let's look at the let. So here I say let a equal 3 and b equals 4 in this expression here. And in Scheme, we would have written in Scheme, we would have written let, and then one pair of parentheses, then the A 3, and then the B 4. And so when you look at them side by side, it doesn't seem to be like a huge improvement. It's a little bit of an improvement, but actually when you look at it in isolation, this thing does look a little bit nicer. Anyway, that's how they do it. Higher order functions were kind of like in scheme again. Instead of lambda, you use fn, which is a definite improvement, right? So you don't have to worry why the heck lambda and not omega or something. So here is fn. Again, argument list in square brackets. We'll see in a minute why. And then here map works the same way. You map this function on this list. You get a list of results. There is a shortcut notation for these functions that looks a little bit odd. So if you have a function with a single variable, with a single parameter, or with one with a couple of parameters, then the shortcut works like this. You use this thing here. Oh, now it wants to work. So, all right. So now I can paint with a mouse. Oh, this is so helpful. Okay, I'm just going to tell you what it is. So you see this pound sign thing here. So it's supposed to kind of look like a lambda if you squint. So and then here we don't have the parameter list. Instead, percent is used for the first parameter. So here use percent twice, and it means use the first parameter. So this means multiplying the first parameter with itself. So percent is if you have one parameter. If you have more than one parameter, you use the thing down here, %1, %2, and again, then you just use the lambda that basically lambda is the main thing, and it's just a shortcut notation that they use all the time. And so over here, this is the squaring function. The function, this thing means function that multiplies the first parameter with itself, and you map it in the usual way. Okay, collections, there's lists. Here I have a quoted list, looks like you would expect. When you have a colon in front of a symbol, that means it's a symbol, it's an atom. And in Ruby, do we have colons?
Symbol, but
Yeah, okay, so many languages. The same thing. Vector is an ordered collection. Vectors have square brackets here. And they have operations. First, of course, they expect the first one, like just like a list has. Then they have a thing called n that lets you get an arbitrary number in constant time. So it's essentially like an array. Square brackets for arrays. Notice that they use a function declaration, so the function gets an array of its argument and not a list. Not for any great reason, except that that the designer feels that the square bracket kind of stand out, and it doesn't really matter at all. You have sets that are done with pound sign and braces, and you have maps that are done with irregular or braces. I guess I'm the feeling that maps are more common than sets. In the maps, you can put in commas to separate the entries. The commas are completely ignored. You could put commas everywhere or nowhere, but they give you a neat way of separating like every second entry out and making the map a little bit easier to read. And all of those are instances of a sequence abstraction. Sequences have first and rest, like you would expect. And unlike Scala, whenever you apply an operation, what you left off is not the original type, but a sequence. So if you take a vector and then you take the rest of it, then the square brackets turn into parentheses because now it's just a sequence. Recursion, of course, the usual way. Here I'm computing the size of a vector. Let's say it's in a very inefficient way. It's just as an example. If it's empty, then it's size 0. Otherwise, it's 1 plus the size of 0. And you see that it has fewer parentheses maybe than a traditional list, but it still does have quite a few. Now, unfortunately, on the JVM, you cannot do tail recursion automatically because it's just not something. It has no way of making it go to. So to overcome that, they say as long as the programmer is willing to indicate when they want tail recursion, then it'll do the CPS rewrite that you're familiar with or somewhat familiar with. And it'll do that when you label things as being tail recursive. So the labeling is a little bit funny. You have to use this loop statement. Loop is just like let. So you have a list of parameters with the initial values, and then you have a body where you do something with them. And then inside the loop, you will want to use this, and of course, in a tail position inside the loop, you will want to use this recur thing and say, run the loop again, and this time make the new x value here, the new y value here. And it's an error if that's not in tail position. It's easy enough to check, and if it is in tail position, then it'll do the rewrite. Otherwise, it won't. So it's as good as you can probably do it on the VM. Scala actually has a similar feature. In Scala, you can say that you expect that something is tail recursive, and then if it can't translate it, then an assertion fails and it won't compile. And there's some people who say, well, this is actually a good feature because sometimes people assume that a function is tail recursive, not realizing that it's not, and then they get bad performance. Here, you have to tell the compiler you intend this to be tail recursive, and you're going to get an actual error as well. Interoperability with Java, that's kind of the most useful feature for people who use it every day. Anything that you can do in Java, you can call from Clojure. The syntax is, there's various variations of the syntax to optimize some things, and I'm only giving you the simplest part. But so if you're interested, you can look it up and see the other parts. So if you want to call a constructor, the easiest way of doing it is with new. You give new, the name of the class. Here I'm giving it fully qualified. I don't actually know if there's some way of doing imports, but for the 2 lectures that we use it, we can look it up. Then you have, of course, all the parameters here, and then that calls the constructor, gives you back the object. Here I'm binding the object to this variable record. Now I might want to call a method on it. To call a method, you use dot, short and sweet. Dot. And the space is actually optional. I felt it was clearer if it was there. The name of the object, then the name of the method, and then the parameters of the method. Couldn't be easy. You can call static methods in a slightly odd way. You have to give the name of the class, the /, the name of the static method, and this particular one happens to have no parameters. That's what this thing here returns an array, a Java array. A Java array is kind of worthless in the world of Clojure because it's this very special kind of construct. You really want to have a sequence. When you hit it with seq, then you get a wrapper around the Java array that translates the secret methods into the methods that are inside an array. So it doesn't actually copy the array. It just gives you a facade over it that makes it look like it was a regular sequence. So the rule of thumb is that whenever you get a Java array, then you should turn it into seq. If you get some other kind of collection, it's fine. Like an array list, for example, it's already a seq. But in an array, you have to do that extra step. Conversely, if you wanted to pass a collection from Clojure into Java, where Java expects an array, you have to use the ch array. So you might say, why is one of them called seq and the other one is called ch array? It's this asymmetry, this deliberate asymmetry that makes it so charming. This, by the way, is again a static method, and it's actually a var args method. It takes an arbitrary number of parameters or you can package it in an object tray like that. So you have pretty smooth interoperability. We're going to be using that in one of the homework assignments where you have to call, get directories and so on. But it's pretty easy. And like I said, some people like the scheme syntax so much that that's the reason they, the Lisp syntax so much, that's the reason they use Clojure. They just want to use that syntax with good old JVM programming. And macros, we're not going to be doing a lot of macroing, but just to show that it can be done. So let's say I want to define a function unless, that's exactly like if, but the other way around. Say if some condition is fulfilled, do something, and unless means if it's not fulfilled. Just as an example. So here's unless, it takes a condition and a body, and if the condition is not fulfilled, then the body should be applied. I can't define it as a function, because if I were to make it a function, then all of the arguments would be evaluated before the function is called. So over here, I want to say unless 1 equals 1, we'll print something. PRN is, by the way, is to print something. And it's not going to work because it's going to first print food and then take the unit value that results from that and pass that on. So it's not going to conditionally print that. So instead, you want to use a macro. And so macros are somewhat easier than they are in Scheme. Use the step macro facility. And unless you have the parameter list, and then you use this thing that you'll remember from your Racket homework, the quasi-quote notation. So you have the backquote, and everything behind here then is literal, except when you have something with comma, then the comma thing gets spliced in. But they can't use a comma, because they already used the comma a few slides back for a space, and so they had to use the squiggle, which is somewhat unacceptable. Couldn't they have had some more foresight and used the squiggle for what? So you can see that this thing has grown organically. And now, this is actually how you used to write macros in Scheme 40 years ago or so. And then someone realized pretty quickly that in this naive macro systems, what happens is you can get name conflicts pretty easily. So if, I'll just show this thing as an example here. Here I have a method that, a macro, sorry, that wants to compute some expression, and then it wants to measure how many milliseconds or nanoseconds it takes to do that. So we measure the time, we evaluate the expression, we do it again, and we subtract what the start. And so over here, we're binding this to this variable start. Now, without the number signs here, there would be the possibility that the expression, which after all is pasted in here, it's not evaluated, it's pasted in here. What if it happened to contain the symbol start? Then I would have changed the meaning of this expression because it would have been captured by this local variable. And this is something that happened in early macro systems all the time. In the Scheme macros, the ones that you've seen, it can't happen. They guard against that with what's called hygienic macros. And here they have like a simple version of that where they force the programmer to say that you need to put a pound sign behind these things and thereby make the name distinct. Every time you make a pound sign, it'll actually systematically renumber it into something that's unlikely to collide with anything at all. So that's what they did. There's going to be some problems with that macro system because if the Lisp and Scheme people come up with this really complicated thing, they must have had it. I just don't know what it is, but but it'll probably cover 90% of the use cases. So that's all you need to know about Clojure to understand STM. And in this lab, I just want you to just get going with the basics so that it's you can absorb it in a couple of days. So it's perfectly easy to use. I've actually had a heck of a time getting it to run an Emacs in a satisfactory way. The simple way doesn't really work very well. The complicated way is a page of instructions. So I think we're not going to do Emacs for this one. So you just start it like this, and you get a REPL, and just paste into that REPL. It'll be good enough for a couple of classes. So I want you to make a file object somewhere where you have two directories and list files. Obviously, that's going to be useful for the homework. And that should be pretty easy. And then that's something that I want for the next lab. I want you to explore the API documentation and for the following simple task. I want you to make a list of 10 lists that contain the numbers from 0 to 100 separated like that. And there is a function called partition that's going to be doing something useful, and figure out how to do that. And then make it a vector of vectors instead, and then write a function so that you get some practice writing a function that where instead of doing a 10 of 10, you make an m and n. And finally, if we have time to do this, which would be nice, we had that size function here. This one is not tail recursive. Okay, why isn't it tail recursive? What's that? Why is it not? Why is this thing not tail recursive?
There is still something,
Yeah.
computation to do
Right.
after it.
If that's that size, I still have to add one to it. And so it's not. So write it in a tail recursive way. And of course, the way you have to do that is you have to have an accumulator value, and then use the loop and recur to do that. Oh, and then finally, demonstrate that you do get an error message when it's not in tail position. So do the loop recur thing, and then tweak it so that it's not that the recur is not in tail position, which is easy enough to do, and then you will see the error message. That's all.